what? The Cj minus Zj ratio, okay? And then the value with the maximum ratio, okay, that variable we enter, and we leave the variable corresponding to the minimum ratio, okay, and that we do iteratively. uh, and the terminating criteria for this process is what? That I mean, when all Cj minus Zj becomes negative, okay, that means now I cannot enter any variable which improves the objective function value. So at that point of time, I have to stop. So that we have seen in the last lecture. So today, let us see how to solve minimization type of problem. Okay, minimization type of problem using Simplex. Now we will say why it is really needed to learn. It is really needed to learn because of one issue. Okay, so let us see what is that issue and how we can solve that. Okay, so you can see there are 3 stages of Simplex, as I mentioned. Okay, now let us take the problem. So I want to minimize such that 3x1 plus 4x2, I want this to be as less as possible. And the constraints are 2x1 plus 3x2 greater than equal to 8 and 5x1 plus 2x2 greater than equal to 12. x1, x2 non-negative. So this is a general thing, right? Whenever you have minimization type of problem, generally the constraints are greater than equal to. Usually, right? Not always. Okay. So, and I want to find minimum value of 3x1 plus 4x2 with respect to this constraint. Okay, so what is the problem? If you apply the same method as maximization method, the problem is as follows. So definitely, I have to remove something positive in order to make this greater than equal to as equals to. So what I do, I subtract some positive value x3 and I subtract some positive value x4, and so that this greater than equals to becomes equals to. These are now negative slacks, okay, because x3 and x4 are positive, so minus x3 and minus x4 are negative, which means this is called a surplus variable. This is a technical name, surplus variable. So x3 and x4 are called a surplus variable. Now the problem here is that if you say initially, what variables are the basic variables? Initially, what variables are basic variables? If somebody could give me an answer. Slack variables, very correct. Okay, I hope others are also agree with Dev's answer. Yes or no? Initially slacks are the, yes, right. So that means x3 and x4 are the basic, okay, and so rest are non-basic. So the x1 and x2 set to 0. x1 and x2 will set to 0. But if you do this, what is the problem? If you set x1, x2 to 0, which means I set x1, x2 as non-basic, then I get x3 is minus 8 and x4 is minus 12, which are not allowed, right? Right, if you set this, okay, x1 and x2 0, if we start simplex table by x3, x4 as a basic, which means x1 and x2 are non-basic, which means they set to 0. So in this, I'll get minus x3 equal to 8, minus x4 equal to 12, which gives me negative value, which violates the non-negativity constraint. So this way, you cannot initialize the simplex table. Okay, and did you get the problem, all of you? So this way, if you start or initialize the table, it would not have the proper initialization. And that is why we need to have something, okay, which helps us in initializing the first simplex table. Okay, so yes, are you getting the issue? If I take a slack, as a basic variable, since they are the surplus variable, they turn out to be negative, which is not correct. This way I cannot initialize. Yes or no? B, Kushal, Urjit, Dev? Yes. So in order to handle this issue, we will use something called a big M. Okay. This also known as a big M method. Okay. So the issue is this. Okay. And now you see the change that I have done. I want to minimize this function. Okay. This same thing can be achieved by maximizing the negative of this function. So since we know the maximization type of technique, how to solve the maximization type of problem that we know, okay? So what I do is I convert this minimize z equal to this by negating. Okay, so what I will do, rather than solving minimization of z, okay, I would rather solve maximization of minus z. Minus z, which means I have to negate the sign of everything in the objective function. So minus 3x1 minus 4x2, and the 0 doesn't matter whether it is plus or minus right now. So minus 3x1 minus 4x2 plus 0x3 plus 0x4, that way. Okay, so and this way I am writing. So I'll solve this maximization problem. Why? Because you know how to solve the maximization problem, right? The serious issue is this x3, x4 cannot be entered. Okay, we can't start the table with x3, x4 as basic variable. So in order to solve this issue, we will add something known as a artificial variables. Okay, so what are the artificial variables? They are not a part of the problem, but we yes, kind of, yes, Urjit. The artificial variables are not the part of the problems. Okay, I write AV. Okay, are not the part of original problem, but we add it to the problem. Why? Okay, but we add. Why? So that we can start simplex. Okay, we can start simplex table, because right now I'm not able to start the simplex table. Okay, that is an issue. So that I want to add something called artificial variables. Then you will say, won't it create the problem? So that will be followed. Okay, don't worry. So what I'm doing is, just to start the table, we add A1 and A2. Okay, so I add some positive A1 and A2, which are called the artificial variables. A1, A2 are not the part of the problem, remember. And this is just done for getting a first table, that is initialization of the simplex table, the first iteration. So remember, now I told you something about M. So M is a very big value. M is a very big positive value, tends to infinity. So I'm not writing something like, you can assume M is, let's say, 10,000, 1 lakh, okay, 10 to the power 6, etc. So M is positive value which tends to infinity. So M is a very large value. Okay, and so here you see what I am adding. Okay, I am adding in this objective function minus M. Okay, minus M into artificial variable number 1, A1, minus M into artificial variable A2. Now why? What is the reason? So see, we must ensure that the rewritten problem is equivalent to original problem. Okay, this problem should not get changed. It should be equivalent to the original problem. Original problem is like this. Okay, but still I am adding this minus MA1 minus MA2. So how can I ensure this, that this is equivalent to the original problem? So let us see the logic behind that. So see, we must make sure, so I need to make sure that artificial variables will not come in the solution. Okay, so in the final solution, whatever after 2, 3, 4, 5 iterations, whatever I am getting, right, in the final solution, A1 should not be there, A2 should not be there, which means A1 should not be as a basic variable, A2 should not be as a basic variable when simplex terminates. So I need to make sure that, okay, that is the first thing. But how do I make sure that this A1 and A2 will not come in the solution at last? So let us see. As I said, m is a large positive value, means m tends to infinity, which also means minus m tends to negative infinity, means it's a very small number, right? So what does that mean? For example, m is 10 to the power 6. Okay, so it is 10 to the power 6 and A1 10 to the power 6 A2. What do you think? If I were to maximize this thing, should I pay attention to A1 and A1 and A2? Because what happens is it's minus 10 raised to 6 A1. Our goal is to maximize. Remember, goal is to maximize. And it turns out minus m A1 in the objective function, minus m A2. And m is very large number. So what happens is, if this goal is maximization, I should not pay much attention to A1 and A2. Because if I increase A1 and A2, this quantity will decrease. Okay, A1, A2 just increases, minus m A1 minus m A2 will come down because A1, A2 are positive. So if you try to increase the value of A1, A2, some positive value, you are trying for A1 and A2, which means minus m A1 minus m A2 will start decreasing. And we don't want that because our goal is to maximize this thing. Okay, so which means that I need to make sure, so I need to keep this m, theoretically this is m, practically this m should be large number, okay, so that A1 and A2 will not come in a solution. So A1 and A2 algorithm will not accept A1 and A2, okay, as a basic as the iteration proceeds, because if it does so, it will decrease this objective value, and you know our simplex is always progressing. Okay, it doesn't decrease, it always tries to progress the answer, maximize the answer. So if it in turn pays an attention to A1 and A2, it starts falling, and which is not desirable. Okay, that's why we use a big value for m which tends to infinity, so that minus ma1 minus ma2 would start falling, so that algorithm will not pick up a1 and a2 in the solution. And since algorithm will not pick a1 and a2 in the solution, if I make sure that, okay, this problem is the same as the original problem, okay, because I'm not giving any importance to that a1 and a2, right? So then why I'm doing this stuff? Just to start the table. Then why I'm doing this stuff? Just to start the table, because earlier I would not be able to start the table. Okay, I hope up to this everybody agrees and clear what I have done. Urjit, Priyank, Rishi, Kushal, Kandar, yes? Keval, yes, okay. Okay, so the rest of the procedure is easy, right? Now it's not, difficult. We have to follow the same process. We cannot start the table without A1, because if you make this x3 and x4 as basic, you see x3 and x4 as basic, your right hand side x3 and x4 as basic, you can see here minus x3 is equal to 8, x1 and x2 will be non-basic, so this will be 0, this will be 0, 0, 0. So what will happen is minus x3 is 8, so x3 will become minus 8, x4 is minus 12. Is this desirable? Is this desirable, Priyank? No. So that is the reason why we cannot start with x3, x4, because otherwise Are you getting, Priyank? Yes, and that's why there is a need of adding artificial variables. Okay, so this is how we can convert minimization to maximization, and now I can use the same method, right? Okay, so what to enter? Now you tell me. This entire stuff I have done for starting the table. So what would be the basic variables in the first table? Priyank, Urjit, what would be the first Keval? Yes, anybody can answer. Which variable? X3, X4? No, because X3, X4 is, that was a problem, right? Earlier. Yes, yes, A1, A2, very correct. Dev, Kushal, Urjit. Minus M, A1 is a objective function value, right? So A1 and A2 are the variables. So A1 and A2 are needed to be entered. Priyank, is that clear or not? The problem was with X3, X4, right? And that's why we switched to other. So the problem with X3, X4 was there. So that's why I add XB. Remember, I will not tell you the entire thing. Okay, whatever the changes only that I will tell you. I hope you are clear with the simplex method. Okay, so you have 6 variables now. X1, X2 were there. X3, X4 were surplus. A1, A2 artificial. So total 6 variables are there. Right hand side and ratio. Okay. Then basic variables, as you told me, A1 and A2 should be basic. What is the coefficient of basic variable in objective function? So you see minus m is a coefficient, right? In objective function, this is minus m, minus m. Okay. So minus m and minus m. Remember, m is a very big value. So minus m is a very small value. Okay. So entire calculation is not based on some taking big values. It's not needed. Okay, we can just take a value m and then easily we can progress. Okay. So now what we have to do? We have to write this 2, 3, minus 1 for x3. So it's 2 for x1, 3 for x2, minus 1 for x3, 0 for x4 because there is no x4 term, and a1 is 1, a2 is 0. Same way for this constraint, I should write 5, 2, 0, minus 1, 0, 1. Okay, so there are 6 variables, so 2 are 0, right? X1, X2, X3 are there, X4 is not there, so 0. A2 is not there, so 0. And right hand side is definitely here 8 and here 12. Okay, here 12. I mean, you get that. Okay, this is how I can initialize the first row, second row, this and this. Okay, these are the coefficient in the objective function. You see, maximize what? Minus 3x1. So minus 3, minus 4, 0, 0, minus m, minus m. Same thing. Minus 3, minus 4, 0, 0, minus m, minus m. Okay, now it is the same method. What I have to do, I have to find the zj. Now zj is the dot product of this with this. So minus 2m plus minus 5m. So minus 2m minus 5m, which is minus 7m. Same way, minus 5m. You can verify it, okay? Then minus m into minus 1, m. Here also m. Okay? Same way, minus m, minus m. And remember, I will not compute this RHS till there is some m term. I don't want this m term in a solution. So if there is a m, okay, because if you do minus 8m minus 12m, there will be minus 20m. I don't want m, okay, because it's not a part of the, entire process. So until you have m, okay, you don't need to calculate this RHS. There is no need. If you calculate, there is no problem even, right? So there is no need. When m is disappeared from this table, I will calculate RHS. Then I will do Cj minus Zj. So now you see, Cj is this minus 3 minus of minus 7m. So minus minus plus, so this becomes 7m minus 3. Same way this becomes 5m minus 4. This is Cj minus, so minus m, okay, minus m, minus plus m, 0. I already mentioned, whatever the basic variables, Cj minus Zj is 0 for that. So a1, a2 are the basic variables. Under a1, a2, Cj minus Zj is 0. That we discussed last time. Okay. Okay, so that way I found Cj minus Z. Now you see, as m increases, okay, as m increases, out of 7m minus 3 and 5m minus 4, okay, 5m minus something, right? 5m minus 4, which value do you think increases rapidly? Asymptotically? Very correct, right? Because 7m minus 3, very correct, first one. So this will increase. So this is a maximum value, okay, of what we can say of Cj minus Zj that we enter. So the x1 is trying to enter the solution. So this is a key column. Okay. RHS is this 8. Divide 8 by 2, I'll get 4. Divide 12 by 5, RHS by the key column, I'll get 12 by 5. Remember, one thing I want to add, you can only compute ratio, okay, when denominator is strictly greater than 0. Okay. If denominator is 0, definitely it's infinity. So that ratio cannot be computed. And if denominator is negative, which means theta is negative. If the theta is negative, means limiting value is negative. It cannot be, because the limiting value cannot go negative. Okay. So I cannot have denominator term, that is key column elements. Okay. So if either of this is, let us say, is in here it is 2, 5, but in place of 2, 5, if it is minus 2, 5, I should not compute the ratio for the negative term. Similarly, if it is 0, then also the ratio is not defined. So remember, only when denominator is greater than 0, I should compute the ratio. Because remember, ratio is nothing but it is a limiting value. Okay, up to what extent I can increase the value so that it satisfies both the constraint. I cannot make those values negative. So I cannot allow ratio as to be negative or infinite. Okay? So remember this thing. Here there is no question, but still I am saying that. Okay. So this is the 4 and 12 by 5. So out of 4 and 12 by 5, 12 by 5 is 2.4. So this is a minimum ratio. So this is a corresponding row, which the variable a2 is a variable which will leave. So x1 will enter and a2 will leave. A variable a2 will leave and x1 will enter the solution. So are you getting what happens? A2 is removed out of solution and the x1 is trying to be basic. Okay? So as per the rule, you try to divide this by pivot. Pivot is 5. Intersection is pivot, right? So this row is divided by 5, okay, which you will get like this. Okay, so I'll just show the second iteration. Okay, the rest iterations I'll just explain the logic. Okay? So this is the thing. X1 tries to enter, x2 left. And how would you compute this value? What is a new value corresponding to this 2? New value corresponding to 2, what it will be? Anybody? Priyank, Urjit, Kushal, Keval? new value, this is divided, right? 5 by 5 is 1, 2 by 5 0, minus 1 by 5 0, 1 by 5 12 by 5, which I am getting. This is clear, right? How? So this is 0, this is 11 by 5. How? Yes, very correct. For this 3, this 3 new value will be, the old value is 3, old value minus, recall the formula, this 2 in the key row, this 2 in the key column, 2 into 2 divide by pivot, t minus 4 by 5. So don't forget that things, right? 3 minus 4 by 5 is 15 minus 4, right? Which is 11 by 5. This will be 11 by 5. So this is 11 by 5. This will be 0. And same way, you have to compute all the other entries. Okay. Say, let us take one entry with m value. Oh, okay. So sorry, there is nothing like that. So this one, you can take the RHS also, 16 by 5. How you can verify? It's 8. Okay, 8 is the old value minus 12 into 2 divided by 5, which means 8 minus 24 by 5, which is 40 minus 24, 16 by 5, which comes here. So I'm not explaining this everything again. Okay, so I hope you can do this. Yes, others? I hope, because that's not others. Can you give me reply? Yes. Okay. Okay. Yes. Fine. Fine. So what I wanted to show, the same way you can start with the ZJ. So you see, I have to do minus m into 0, minus 3 into 1, so minus 3. Now you see, minus m into 11 by 5 plus minus 3 into 2 by 5, so which is minus 11m minus 6 whole divided by 5. Then you do Cj minus Zj. So Cj is minus 4. Okay, minus 4 minus of entire this. So it would be minus 4 plus 11m. If you take a minus common, this will be there. And if you solve this, it will be minus 20 plus 11m plus 6. So 11m minus 14 by 5. I'm taking whole minus common, and minus minus will be plus because I'm doing Cj minus Zj. Okay. You can verify that under A1 and X1 you have identity matrix A1, X1, and Cj minus Zj is 0 when A1 and X1. This is very important, okay? Otherwise, there is something which is not desirable. I mean, wrong, rather. RHS no need to compute because still there is a M. In CB, there is a M. So I don't want that. So now what you will enter? So you see, the highest value is 11. Okay, this minus 14, minus 3, they are actually not very significant, right? Because M is larger value, so 11M is very large value. Okay, so this value, rather than other constant, okay, even if here it is 15, right? Okay, or sorry, even if here it is 2m minus 3 divided by 2, this is the 11m minus 14 divided by 5. This is a more value which will enter. So x2 will enter to the solution. And so this is a key column. What will leave is, if you find the ratio, both are positive, so I can compute the ratio for both. It is 16 by 11 and 6. So 16 by 11 is lesser, so this A1 will leave the solution. Now if you enter x2, and if you leave A1, I'll get X2, X1. And if you do this process, okay, finally, I'm getting X1 and X2 as basic. And now you see, I get 16 by 11, 20 by 11. You do the calculation by yourself. I'm not telling that. Okay. So, and finally, you see this entire Cj minus Zj are all less than equal to 0. This is negative, minus m, it is negative because m is positive, this is negative. So this is a terminating criteria. When all Cj minus Zj comes out to be negative, you should stop. What are your solutions? X1 is 20 by 11. This is how you read, right? X2 is 16 by 11. Okay, so X2 is 16 by 11, X1 is 20 by 11. Now you see in the table number 3, there is no artificial variable. There is no A1 and A2 doesn't come as a basic. These are the basic, right? In basic variable, it turns out to be just X1 and X2. Okay, and I get X2 equal to 16 by 11, X1 is equal to 20 by 11. Okay, now finally, up to second iteration, I was not calculating this RHS. Now I need, because there is X2 and X1. There is no A1, there is no A2 in the final solutions. So what I do, minus 4 into 16 by 11 plus minus 3 into 20 by 11. So 64 plus 60, which is minus 124 by 11. And now you see, you will surprise why this is negative. Okay, Z is minus 124 by 11. Yes, any reason? Janil, Janit, Dev, any reason? Can you identify? The objective value is negative. Yes, this is positive, X2, X1. This happened because I modified a minimization problem, Z equal to 3x1 plus 4x2. By negating this value of Z, I take a maximization problem and I solve maximization type of problem. So remember, the variables are same. So if you solve this x1 and x2, okay, they are the same. The answer is same. So remember, minimization of fx, okay, and maximization of minus f of x, okay, will give same solution. Whether will give same solution. Same solution means the values of x1 and x2 are same, no matter which problem you solve. But the value of objective function, okay, at optimal x1, x2, at optimal x1, x2, okay, will be reverse in sign. Okay, so actually, see what happens is value of objective function, it's a minimization of fx and maximization of minus fx. If you solve any of these two, x1, x2, whatever you are going to get, they are same. Okay, but the objective function value, if you put x1, x2, right, they will be different in sign, because in one it is plus f of x and second is it is minus f of x. So if I want to get the actual solution of minimization, I should consider this negative of this z. Okay, so we need to negate the z to get the optimal objective value, which means it should be plus 124 by 11. So why? Because original problem was maximization. We converted maximization by putting negative sign to the objective function. So we solved maximization. Okay, so we will get a negative sign in the objective function value of z. For z value, you are going to get negative sign. So to get the correct value, we need to negate that. Okay, let us see there also. Remember this x1 is 16 by 11, 20 by 11, 16 by 11. Okay, x1 is 20 by 11, x2 is 16 by 11. That solution I am getting. Let us put it in the original problem. Okay. If you put this, okay, x1 equal to 20 by 11, it will be 2 into 20 by 11. So 40 by 11. And if you put x2 is 16 by 11, so 3 into 16, 48 by 11. And you can do this, 40 plus 48 is 88 by 11, which means exactly 8. And 8 greater than equals to 8 is correct. Okay. Same way, you can also put the values here, 5x1 plus 2x2. So 5 into 20, which is 100 by 11, plus 2 into 16, 32 by 11. So 100 plus 32 by 11. So 132 by 11, it is what? Exactly equals to 11 ones are 11, 11 twos. So 12, exactly equals to 12. So 12 greater than equals to 12. That is also correct. And if you put this value, x1 equal to 20 by 11, okay, in objective function. So 3 into 20 by 11, 60, plus 4 into 16, 64. Okay, divide by 11, which is 124 by 11, which was the desired answer. Okay. So remember, solutions are same. Solution x1, x2 is same, but value of objective function, if you have converted minimization to maximization, to get original answer, you have to negate that answer, so that I can get the original answer back. Yes, everybody clear what I'm saying? Priyank, Abhi, Urjit, others? Yes. Okay, fine. So remember, this is the way how to solve the minimization problem. Remember, if you are asked what is the problem with minimization problem, why can't I do the same method as maximization? The answer is table cannot be initialized. Why? Because negative values for the slack. So that what we do, we added artificial variables, but I don't want them to be in the solution. So what I do, I take a big value of those artificial variables, I converted minimization to maximization, and so it will turn out to be minus MA1 minus MA2, this kind of thing. So the algorithm will not pick A1 and A2 in the solution. Why? Because if it picks that A1 and A2 in the solution, it will decrease the answer. And my goal is to maximize the answer. So rather, algorithm avoids A1 and A2 from being in a solution. This way, I avoid it, A1 and A2. And still, the problem is same as the original problem. Okay. So this is a new thing. This method is also known as a big M method. This is called a big M method because for M, we are using a large value. We are actually not taking any value for M, right? Writing just M. Okay. So remember, big M method is very useful when you are given a minimization type of problem with the constraint greater than equals to. So remember, greater than equals to, whenever it is coming, it's a problem because you have to add negative slack and that you cannot enter. Are you getting what I'm saying? If the constraint is greater than equals to type, you have always a surplus variable, and so that you cannot start the table. So whenever it is like that, you need to add some artificial variables. Am I saying correct or not? Rishi, Abhi? Yes? So greater than equals to type of constraint is serious problem, right? If it is even in a maximization type of problem, if you have greater than equals to type of variable, it's just still a problem. Okay, we will see that type of example. Okay, so now let us move ahead. Okay, so my second question, this I address the first concept, that how to solve minimization problem with greater than equal to type of constraints. Remember, in practical, linear programs are mixed constraints. Some constraints are less than equals to type, some constraints are greater than equals to type. Objective function can be maximization, could be minimization. We cannot assume anything. That type of linear program is called a mixed linear program. Okay, we will also see that type of example, how to solve. But I will address the second question, how to detect unboundedness in Simplex. In Simplex, till now, whatever the problems that we have seen, all having some solutions, right? Some sort of solutions. Then how to detect unbounded linear program, right? In earlier lectures, we have seen what is unbounded, right? I can increase x1 and x2 indefinitely, and I can get better and better and better value. So I have no actually the true optima. Okay, I can go ahead again and again and again, and I can get infinite in that direction. That is an unboundedness. But how to solve that? Graphically, you can detect, but how to solve it using Simplex method? So let us see that. So for that, I am taking some unbounded problem purposefully so that you can understand. Okay. Let me first tell you that it is indeed unbounded so that it is easier for you to understand. The problem is simple, maximization 10x1 plus 9x2. Constraints are also simple, less than equal to. So, I mean, it's a very simple problem. x1 minus x2 less than equal to 5. 4x1 less than equal to 24. You can also write x1 less than equal to 6. Okay. x1 less than equal to 6 in place of this. That is also correct. Now, if you see the graphical method, this is a line x1 equal to 6, vertical line. This is an x1, x2 plane. x1 equal to 6 is a vertical line. And x1 minus x2 is equal to 5 is this line, which passes through 5, 0 and 0 minus 5. And this is an intersection of line x1 equal to 6 and x1 minus x2 equal to 5. So this point must be 6, 1. Okay, because it satisfied both x1 minus x2 equal to 5 as well as x1 equal to 6. 6, 1. And remember, my constraints are less than equal to type. So this is my feasible region. x1 should be less than equal to 6. So this shaded region, this type. Okay. And x1 minus x2 less than equal to 5, which means this type of region, this particular region. x1, x2 both are non-negative, so greater than equal to 0, 0. So this is the shaded region having 1, 2, 3, 4 corner points, but it is unbounded. You can see I can go infinitely in this direction. Still, it will satisfy both the constraints. Okay. You see, just for, let us take x1, 3. And x2, I can take 100. I can go in ahead in this direction, So x1, 3, x2, 100, will it satisfy all the constraints? x1 minus x2 less than equal to 5. Is it satisfying that? Yes. 3 minus 100, minus 97. It's less than equal to 5. Yes, very correct. And x1 is less than equal to 6. Yes, x1 is 3, less than equal to 6. That is also very correct. So both the constraints are satisfied. Am I saying correct or not? Urjit, Abhi, yes. So that means, but Kushal, can I increase this x2 value from 100 to 200? Still, both the constraints will be satisfied? Yes. Somebody can give me 500, 1000, 1 lakh. So that means in this direction, I can go in infinite. I can go in infinitely in this direction. I can increase x2 value indefinitely. Still, all the solutions are feasible. This is an unbounded linear program. Okay, it's unbounded linear program. So all of you agreed that this is unbounded. Yes or no? There are 100 students approximately. Agree na? Yes. I don't know what about remaining 80 students, right? But you are there. So now how to detect it? So start simply the table as usual. I add a slack x1 minus x2 plus x3 equal to 5, and I just keep 4x1 is plus x4 is equal to 20. You can also write x1 plus x4 equal to 6. Okay. So now you see. So initially I enter x3, x4. There is no harm in that because they are positive slack. So x3 equal to 5, x4 equal to 24. That is allowed. Positive values. Coefficient of x3 and x4 are 0 in objective function. So 0, 0. Now see carefully. This is very important. Okay. Tabular method. Write 1 minus 1, 1, 0 from first constraint equal to 5. 4, 0, 0, 1 equal to 24. 4, 0, 0, 1, 24. Coefficients are 0. Now do directly Cj minus Zj. Zj is directly 0, 0, 0, 0, right? 0, 0, 0, 0. I have not written that, right? Because this is 0. So Cj minus Zj is same, 10, 9, 0, 0. The maximum value is 10. So I can enter this variable. So this becomes my key column. So I divide 5 by 1, I get 5. I get 24 by 4, I get 6. I can do that because 1 and 4 are positive. Okay. So 5 by 1, 5, 24 by 4, 6. Minimum ratio is 5. So I have to leave this variable. So this is 1 is my pivot. Okay. This is a leaving variable. X3 will leave and X1 will enter. X1's coefficient is 10. X4 is 0. Divide by 1, nothing will change. 1 minus 1, 1, 0, 5. Now you see, you apply that formula, right? This is a key column and this is a key row. And if you apply this, this will definitely turn out to be 0. 4 will become 0. 0 will become 0 minus minus 1 into 4 by 1. The old value is 0. For this 0 I am talking. 0 minus minus 1 into 4 by pivot. Pivot is 1, which will be plus 4. That way you simply can do this. I'll get this. Parallelly, you can verify, okay, whether I have done all calculation correct or not. Okay. So 4 minus 4, 1, and this will be, you see, 24 minus 5 into 4. This will be right for this. 24 minus 5, okay, into 4 divide by 1. So 24 minus 20 it is. But surprisingly, now you see, here you calculate Zj, okay? Zj will be 10 here. It is minus 10 here. It is 10 here. It is 0 here. So Cj minus Zj, sorry, Zj will be here 10. So 10 minus 10 will be 0, Cj minus Zj. Here it will be minus 10. So you see, it is 9 minus minus 10. So 9 plus 10, 19. 0 minus 10. So minus 10. And 0 minus 0, so 0. So yet you can enter, right? Something is positive. So you can enter this. So you can see, I can enter x2. Enter x2. And but surprisingly, you see this is negative. So this is my key column. And now you see this is negative. So in 5 divided by minus 1, I should not do. That's why I put a cross. Why? Why you can't do? because this denominator is negative. What's the problem with negative? This theta indicates the limiting value, okay, that we discussed. And I don't allow that values to be negative, right? Or that's why you should always ignore them. Okay? Because even if you do that, it will not lead to the betterment of the solution which satisfy all the constraints. That's why prevent this. So remember, but yes, I can do still this thing. This is positive. 4 by 4, the value is 1. So ignore those rows which are crossed in theta column. So there is only one row left, which is x4. So I have to compulsorily leave this x4 from the solution. Remember, I don't have a choice. There are just two things, x1 and x4. For x1, it's cross. So I cannot opt that. So I have just the one choice, that leave this x4. So enter x2, leave this. So you will think this is what we want, right? Ultimately, I want x1, x2 in the final answer. Okay. Yes, but the problem, the serious problem is here. So you see, this is my key row. This is my key column. Okay. And I mean, if you divide the key row by the pivot is 4, it will be 0, 1, minus 1, 1 by 4. Okay. And same way, if you do the operations, I'll get here 6. One very important thing, x1, x2 are basic, so under that there is identity. This is not going to change. x1, x4 are basic, so under x1, x4, you have identity. Okay. Now you see, now if you find Cj minus Zj, you see this is 10, x1 is 10, 9, 0, 0. So Z, so x1, x2 are basic, so here it should be 0. Here 10 into 0, 9 into minus 1. So minus 9, 0 minus minus 9, it is plus 9. Same way, 10 into 1 by 4, 9 into 1 by 4, 19 by 4. 0 minus 19 by 4, minus 19 by 4. So now you see, still it is not terminated. It's not terminating. There is x3 which tries to come again. Remember, x3 was initially part of basic. Then it left, x1 came. Then x4 left. And then x2 came. Now x3 again tried to come. And one more thing, so this is kind of a key column. But ratio is not possible. You see, 6 divided by 0, I cannot find limiting value. 1 divided by minus 1, it's negative. I cannot find a negative. So what does that mean? What is your conclusion? Yes, Keval, can you conclude something? At this moment, what is your conclusion? X3 tries to enter. There is a scope of entering because X3 is positive. Okay, this is, yeah, there is a scope of entering. But there is nothing to leave. Okay, you cannot leave these crossed columns. So you find a key column, but there is no key row which can leave. I mean, x3 coming again in the solution, but neither x1 can leave because there is no theta defined for that, nor x2 can leave. A variable trying to come to the solution, but no variable can leave. Okay, so this situation, okay, this is this criteria. Remember the rule, or you can say the method to detect unboundedness. If there is something which we can enter, okay, which we can enter. Something means some variable which we can enter, but none of the basic variable can leave. So, variable is trying to enter to the solution, but there is no variable which tries to leave the solution. Okay, out of existing basic variables, there should be some basic variables that should leave and make a space for new variable which is trying to enter. But that doesn't happen, which means here it is it's unboundedness. case unbounded linear program. Are you getting this criteria? Keval, Rishi, what I'm trying to tell? Okay. Normally what happens? Normally what happens? We terminate. When do we terminate? Normally, when do we terminate this program? When all Cj minus Zj are less than equal to 0, we terminate, right? But here it is surprisingly, there is something which we can enter. There is nothing to leave, which means, remember, x1 and x2, okay, objective function will never leave feasible region. This 10x1 plus 9x2, okay, will never leave the feasible region, and algorithm thus says it will terminate and shows unboundedness. Remember, if you start with a program and ended with a scenario like this, there is something to enter, but there is nothing to leave or left. This condition says about the unbounded LP. Okay. Yes, everybody got this? Rishi, Priyank, Janil, Janit, Hasti, Dev. Yes. Okay. Okay. Fine. Okay. So tomorrow we will see for more next type of scenarios and linear programs and how to solve. Okay. Thank you so much. With this, I end.